Okay, according to my clock, it's time to start. So, happy Friday. Okay, so I have some things to talk to you about. As you know, at this point, I hope MP6 is not due tonight. It's due tomorrow night. So instead of just ruining one evening of your weekend, we're satisfying our goal of ruining 2 evenings of your weekend. So go us. Are you waving to me, Gabe? Hi, Gabe. I hate it when that happens. You think somebody's waving at you and you wave back and you're like, oh, like this. All right. I think what you really want me to talk about for a few minutes, hopefully coherently, is exam 6. So Wade and I sat down. We were going to make a list of exam questions, and by rights, the exam should be focused on MP6, that is KD trees. And we decided that we couldn't come up with enough variety of questions. We couldn't come up with enough sort of similarly difficult questions, and all the questions that we liked a lot we felt like were too hard. So what we decided to do instead was to make this an exam where we basically give you an abstract data type or an interesting, and by that I do not mean difficult, but an interesting problem to solve, a new problem to solve, and ask you to design the solution. So we'll see how that goes. We think we found some kind of cool problems, but they will be less like things you will necessarily have seen before. It's more of a creative exercise. Now, that said, we admit that this is sort of an exam of a different flavor. Oh, and there will only be one question of those. We admit that this is an exam of a different flavor. So, like all of them, when the data does come back, if it looks like, whoa, that was an experiment that failed, we'll normalize those scores, and exam 7 will still be something that you can use to alleviate one of the other exams too. So we don't want to both give you the benefit of exam 7 and simultaneously force you to burn exam 7 on this current exam. So it's in all likelihood, our intention will be that you'll be able to use exam 7 to recover from an earlier exam. I don't know that that will be true, and it will depend on the data that comes from exam 6, but we know this exam has a little bit of a different flavor. At least when I talked to Wade yesterday, that was the intention for it, and I haven't heard differently. All right, are there any other questions? So if you've been following along and you're connected to the class, you're going to come in, we're going to ask you to write a little bit of code, and you'll leave and you go, oh, okay, done. Okay? Yeah?
For exam 7, is there going to be a sheet where we have to pick which exam?
Oh, yeah, let me tell you how exam 7 is likely to go. You'll open up exam 7. There will be 6 problems for you to choose from. Each of those problems is a replication of a previous exam. Okay, so you don't have to make your decision until you land on that splash page. You don't have to. Probably you should come in there with knowledge of your previous scores so that you can decide which of them to take. Yeah? Yeah, exactly. So, I mean, we may give you a little bit of scaffolding, like, here's a tree, change it to do this, add this functionality. So we might give you the node stuff, for example, if it's a tree-based thing. We'll give you stuff that you might find useful, I hope. So if that's what they look like. But the idea is for you to wrap your head around something that you learn about in that time. Okay? All right. Any other questions about this? Exam 6? Yes? Or 7.
So for exam 7, it's just one question?
Exam 7 is a retake of one exam.
So you said it's
Yeah, 6 different questions. Each one, it's like hierarchical kind of. Or maybe it'll be 6 different headings and there'll be 2 problems. I'm not sure what the interface looks like. But the point is, the larger point is, for exam 7, you will get to the testing center and decide there which one of them to take. Okay? And you won't be able to go, okay, which one of these is easiest, right? No. I don't know how to prevent that. Well, we'll work on it. Our intention is for you not to be able to like open up a bunch of them and go, oh, look at exam 2. Let's go. All right. Finally, what do you want to do?
Yeah, so just a quick announcement about Lecture Helper. So, of course, it's available if you want to ask questions, but right now we have the survey open. So that it's really easy, less than 5 minutes of your time, and it's just, there's a Piazza post about it. It's lecturehelper.cs.illinois.edu/survey. So if you would just go to that and complete the survey, please make sure you're logged into your Lecture Helper account so you get the right survey. Yeah, do you guys have any questions about that?
The right survey meaning you're enrolled in this section versus the other section
Yep.
of the class.
So if you just check the title, it should say 2 p.m. lecture versus 11 a.m. lecture. Yeah. Okay.
Please do that for us. So my husband is currently teaching CS 105 this semester, and he asked the class for a volunteer, and somebody actually raised their hand and said, is there extra credit involved? And what I suggested he should do is say, well, how much extra credit would you like? And that person might say, well, 5 points of extra credit, and then it should become a bidding war. Because then somebody else will go, well, I'll do it for 2 points of extra credit. Well, I'll do it for... So this is, the lecture helper thing is, I'm not going to give extra credit for it. It's for the good of improved instruction going forward, and we all know that's a good thing. So, all right.
That's a good point. Yeah, no extra credit.
But our love forever. Yeah? Uh-huh. Okay, so there's like this many questions there, okay? So test cases that we give you will not necessarily be exhaustive, but, and if we have done something different than what I'm about to say in the past, then we should talk and you can like educate me, okay? But maybe after class perhaps, because I'm happy to have the conversation, but you know. So I think that the test cases that we give you are not necessarily adequate. Okay, so you don't know how you did exactly when you leave the test. But if you are compiling and passing those, you should get significant extra credit provided you don't change the things you shouldn't have changed. So you can make your code compile sometimes by, like, say, adding a helper function into the .h file, but we don't grade the .h file. So you would have passed the test cases that we gave you, but in a way that is completely different than the grading that we do. Does that make sense? So I'm not going to promise that if your code compiles at the testing center, it will compile on our grading scripts, because I don't know what you would have done to make it compile at the testing center. Do you see what I mean? So our intention is that if you write the code in the way that we prescribe in the file that we grade, it will compile in the testing, in the evaluation environment, and the tests that we have given you will be a subset of the tests that we deploy. That is our intention. If something has been different than that in the past, you should talk to us because we can fix it, okay? Does that answer some of your question? Okay. Hit me with another.
So in one of the exams, I passed the CS4 test.
Uh-huh.
And then still got 0 that question.
for that question. So that feels to me like a problem. If your interpretation of what happened during grading is correct, then that is certainly not, so we want to know about that, because that's certainly not what we want to see happening, okay? So yeah, talk to us, because that doesn't sound fair to me either, and we're happy to fix it, okay? But let's do that online, and that goes for any of you, right? Like if you go, well, look at this. My code does the right thing on all of these test cases, and you didn't deploy those test cases, and we think we did, then we should know that something's broken in our evaluation scripts, okay? And yes, please do, like, contact us. Have you already contacted us? No. Okay, do so, please. Yeah? So you can either email me or email Wade. Usually if I see that my name's the only name on there, I fire it off to Wade immediately. Or you can post privately to the Piazza, because what happens then is that course staff feeds it into the Slack, which gets all of our eyes on it. So, and we're making a list of all those different things. So, so I have a couple questions here. If we fail exam 7, so if you read the email that we sent you, the grade that you get to stand in for exam 7 is the maximum of the exam you're retaking, the average exam, and the one that you take. So let's see. Oh, does the lowest grade get bumped to the average also? No. Does not. Not in the formula that I sent you. Yeah, not in the formula that I sent you. Would I think about that? Oh, I hadn't thought about it before, and I'm not going to change any policy standing at this point in the room. But I'll think about that. All right, any other questions? Update on exam 6, I just did that. Oh, that was from last time even. Okay. The other comment is that lecture helper is great. Yay. Okay. All right, so I have a picture for you. Last year when we had this exercise, the AV system was down, and so I called for volunteers, and we did a human pyramid in the front of the room. We're not going to do that today because the AV system is not down. But what I want to know is, why did I put this picture of a human pyramid on today's first slide? Why is it there? Because it looks like a tree. Yeah, partly. At least if you just glance at the top of it, it kind of does, right? Okay, good. Okay, what? It's a heap. In what sense is it a heap? So that's right, that's the answer I'm looking for. This image reminds us of a heap. Why? Why does a human pyramid remind you of a heap? Yeah? Yeah? Yeah, look it. So the people at the bottom are probably stronger, which probably correlates with size, than the people at the top. And so in some sense, these numbers are bigger than these numbers. In every human pyramid that I have ever made in any playground or backyard or living room in my entire life, the very first question that everybody decides upon collectively is, what is it? Who's on the bottom, and then followed shortly by who goes on the top, right? Like there is this automatic semi-sort into who's down there and who's right there, right? Yeah?
Also, it's possible to remove any of the people like in the middle of the tree without destroying the tree.
Oh, yeah, very good. So the observation is you could not take that person out of the structure. And true, like many of the trees that we have implemented, we don't have immediate access to any of the data down low in the structure. Though if it's in an array, it's not too bad. All right, so this is a metaphor. This is a metaphor for our data structure. where does it fail? Where does it fall down? How is it not really a metaphor for a heap? Yeah? Yeah. Yeah, so look at the size of each row here is changing linearly, right? It increases by 1 each time, whereas in a heap, the sizes of each row change how? They double, that's right. So the number of elements in each row is exponential in the case of a heap, but only linear in the case of a human pyramid constructed in this way. And in fact, if you say each person is a node, and a node's children are the people whose shoulders they're touching, then this thing isn't even acyclic, right? Like it's really a lattice structure on a graph. Okay, any other observations or questions about this? About the metaphor? All right, so a heap is one way we can implement abstract data type what? Priority queue, good. Whose functions include remove. For us, it's remove min. I could just, an analogous statement there would have been remove max, and that should not blow your mind at all. What's the other one? What's the other function? Insert, good. Each of those have running time. Each of those have running time. At the count of 3, everybody say it together, okay? 1, 2, 3. Log n. That was lovely. Was I really the only one that spoke? Yeah? Okay. Thanks. Nice. Okay. All right. So last time we had sort of branched off of heaps, and we were talking specifically about a practical matter. And that practical matter was, how do you make a heap if somebody gives you a bunch of data in an array and says, oh, I need to use this thing for a priority queue? You say, just 1 second, I'll build a heap for you. We talked about 3 different algorithms to do so, 2 of which are totally intuitive. 2 of which, number 1 of which is, heck, just sort the thing, right? The second of which is, okay, I know how to insert into a heap, so let's just insert each element 1 at a time into the heap, okay? Both of those resulted in running time, big O of n log n. I won't put the pressure on you guys to say it this time, okay? So each of those resulted in the running time of n log n. And I said, oh ho ho, I have a better strategy. It's a provably better strategy, and after we review what that strategy was, we're going to do the proof that it's better, okay? All right, so somebody gives me an array of data. Oh, pretend this is the array of data originally. Okay, so W actually lives there. So somebody gives me an array of data, and I go, whoa, that is not a heap. Let's make it into a heap. The first thing we do is recognize that for our simple implementation of a heap, we need the first cell to be empty. Then we do the following. I'm essentially animating this code up there, okay? The code doesn't start until I pay attention to the fact that these leaves, these red nodes, are already heaps. They are already the root of a structure which is a heap. And I'm not going to worry about them in the rest of my algorithm, okay? So let's see. So I'm good. All of this is good. I'm going to start off my algorithm at the parent of W, which is here. And then effectively, I'm going to heapify down from each one of these, because heapify down from H will assure that everything below H is a heap. H and below is a heap. Heapify down from D will assure that that subtree is a heap. Heapify down from L will assure that that one is a heap. I'm not going to actually do the key swaps here, okay? Things get more interesting, I think, here with the observation that I has two children, and they might be arbitrary size, right? I has two children which are definitely heaps. Calling heapify down will assure, again, that all of this is a heap, okay? Similarly for you, and then finally at the end for the root. So we stop, so I starts at the parent of the last thing and goes down all the way to the first thing. Heapifying down all the way, okay? Any question at all about that algorithm? Okay, so I want to make the following observation. The observation is simply that we are iterating over, each node, and the work that we incur at each node is proportional to the height of the subtree for which it is the root, right? Because I'm calling heapify down from here. So the amount of work that we might incur is proportional to the height of the subtree for which this is the root. Okay, you buy it? Just go, everybody go like this if you buy it. Or go like this if you absolutely do not, no way. Okay, or just do this. That would be okay too. All right. So D, when we get to this point in the for loop, the amount of work that we are going to incur is proportional to, in the very worst case, D might have to swap all the way down. That all the way down is measured by the height of the subtree for which it is the root. Got it? Okay, so, and that's true for all those nodes. So, here's how we're going to measure the running time. So what we're going to justify is that the running time of build heap on an array of size n is big O of n. Here's how we're going to do it. Instead of focusing, I hate it when people read off their slides. Instead of focusing specifically on running time, we observe that the time is proportional to everything I just said 2 minutes ago. The sum of the heights of all of the nodes, which we denote by S of h. Okay? Any question about that? All right, so we're going to write a recurrence because recurrences are easy. Start with the base case. What is the, for a heap of height 0, what is the sum of the heights of all of the nodes in a heap of height 0? Sum of the heights of all the nodes in a heap of height 0 is 0. And in fact, that corresponds to the amount of work we do on a single node, right? We do 0 work. Okay, fine. And, yes? No, we don't. No, we don't. We refer to them as 1 plus the maximum of the heights of their children. 1 plus -1 is 0. Yeah, okay. All right, so let's look at the recursive case. I don't know what the sum of the heights of all of the nodes are in a heap of height h, but I know that it's no more than the sum of the heights of all of those nodes, which is what? What of h minus 1? S of h minus 1. Good. Plus the sums of the heights of all of those nodes, which is, again, in the worst case, S of h minus 1 plus, I'm trying to add up the heights of all the nodes. Yeah? It's one node, but I'm not adding up the existence of that node. I'm adding up the heights of all the nodes. So, h, that's right. To be fair, I heard more ones than h's originally. So, all right, is that clear? Okay. All right, so that's a recurrence. We could solve it. Have you seen that recurrence before? Have you seen it before? Kinda looks like what recurrence? Kind of looks like the merge sort recurrence, except that in the merge sort recurrence, instead of h minus 1, it's n over 2. And it turns out to be important. Okay, so a few years ago, maybe a really long time ago, I puzzled and puzzled over this recurrence. And I came up with this as the solution. Now, I think you could do this too, if you wanted to, minus h minus 2. I don't know why it's so funky. But we don't have time for puzzling over recurrences right now. What we do have time to do is verify that I haven't somehow forgotten what I was supposed to write there. That is, we can verify very quickly that this is actually the closed form solution to the recurrence that we have written above. Okay? So how do we do that? Say, let's prove it by induction. Okay? All right. So proof of solution to the recurrence, and that's an inductive proof. It's probably going to be the fastest inductive proof you've ever done. Remember that in an inductive proof, we take these things as given. Okay, the recurrence is given, and this is what is mysterious. This is what we want to prove. Okay, so first thing we do is we address our base case. That is a case where h is equal to 0. The recurrence gives S of 0 equals 0. The closed form gives, S of 0 equals, 2 to the 0 plus 1 minus 0 minus 2. Did it work? Okay. Equals 0. Yay. Okay. Any question about it? So now let's look at the general case, or the inductive case. And in this case, h is bigger than 0. The recurrence gives S of h equal 2s of h minus 1 plus h, but I think we can do a little bit better with that. What could we do better with that term? What could we do? What should we do with that term? That smaller term? Should we do? Yeah? Yeah, look, so I'm not going to write the inductive hypothesis, not for things as simple as this. I'm just not going to write it down. Don't tell Margaret, okay? Because we understand that the inductive hypothesis simply says that this expression holds for any value less than the one we're arguing about. And sure enough, look, h minus 1 is less than h. Yay. So we're going to substitute, that is, here, I'll write it like this, J. We're going to substitute h minus 1 into the original theorem, okay? So this is then 2 from before, and then S of H minus 1 by inductive hypothesis is 2 to the H minus 1 plus 1, because, yeah, minus H minus 1 minus 2 plus H. Don't forget this guy over here. Okay? Now this will take you about 3 seconds, but you'll collect all the terms and ultimately you will write down this expression. Okay? Any question about it? Because you've got, you know, minus 2 H's plus an H. There's that. You've got minus you've got plus 2, wait, oh yeah, plus 2 minus 4 here, so that's minus 2. And then this one is just 2 times 2 to the H. So there you go, okay? So we're happy, yay. But nobody wants to hear about the running time of our algorithm in terms of the height of the structure. Everybody always wants to hear running times in terms of the amount of data that they hold. And so, since we know that h, the height, is less than or equal to log base 2 of n, we're going to argue that the running time then is less than or equal to 2 to the log base 2 of n plus 1 minus log base 2 of n minus 2, but that's just, those are just constant terms, it doesn't matter. What is this? It's just 2n. This is less than or equal to a constant times n. So this is big O of n. Okay? Any question about it? Whoa! How did that happen? The upshot is, it happens because, you know what? Only one of those nodes incurs that full log cost. Half the nodes in the tree, half of them, full half of them are leaves. There's no work at all for all those leaves, right? It's only, and look at the yellow ones. That whole level only does at most one swap. Okay, no big deal. All right, any question about it? Whoa. Any question about it? Yeah? Yeah, but we're doing an upper bound, so it doesn't hurt anything to go to do the 2 S of H minus 1. Okay? So yes, sure, go ahead, but you don't have to. Okay, we can be loose. All right, anything else about this? Okay. So it turns out that heaps are interesting in their own right, not just because we've got this kind of interesting way to build them, but also because we can use them to sort data. So this is independent of the priority queue application of heaps. This is a new kind of sorting. As you well know at this point, the purpose of sorting is to take an arbitrary collection of data and to return it to the user in sorted form, okay? Our interface is going to be, our intention is that we're going to hand back the data at the start of the array in sorted order, okay? Increasing or decreasing, I don't care very much. You can tell me that at the end, okay? All right, so what I'm going to assume is that our strategy for this is to, number one, take that input data, that arbitrary array, input an arbitrary array of comparable data, and build a heap out of it. Okay? And that's the point at which this data, this illustration comes into play. So we have already run the random array through the build heap algorithm, and this is what we ended up with. And if you remember, that first element is blank. Okay? What's the running time of that? On the count of 3, we can all say this. 1, 2, 3. Yeah, we all said different things, huh? I'm going to say big O of n. All right. Now, here's where the algorithm gets interesting. All we do is remove min, remove min, remove min, remove min, etc. until we're done. And the place we put the data is in the back of the array. Why not, right? So when I say remove min on A, W gets swapped up and reheapification occurs to the left, but this cell is now available, right? This cell is available because effectively I'm removing W. I'm using it as glue to glue the two heaps together like we talked about before. And so I can put A here. After that, B will be in the root. Okay, I'm not going to rebuild the heap every time, but B will be in the root. After removing A, B will be in the root. That's what happens. And we can remove min again. So we remove B, plunk it down in the last cell, and observe that heapify down will restore the heap property to everything to the left of B. Okay, etc. Any question about how that works? Yeah? Say it again. Where does W, so originally, in the original algorithm for remove min, W is swapped up to the root, and then we call heapify down, which swaps with its smallest neighbor, swaps with its smallest child, and heapifies it down in the structure. So I don't know. The answer is I don't know where W is, but it's somewhere in this heap, okay? So I'm assuming that you just kind of go, okay, there's this amorphous heap there that we're building, okay? What I do know is that because I can tell by looking, W in the end is going to be the last thing that we remove, right? Because it's the biggest thing in that structure, U, V, W. Yeah, Jeremy? Yeah. Yeah, well, let's talk about that, okay? All right, so when this algorithm finishes, we're going to write repeated remove min here. When this algorithm finishes, we'll have W, then U, then the keys in reverse order. Now, that doesn't bug me so much because, you know, whether or not that is what the user wants depends on what they want, right? Probably, though, they want them in increasing order, and almost certainly they don't want an empty spot right here, right? Almost certainly that's, if you got your data back and all of the first one, it had shifted over, you'd be like, why? Why did that happen? So we're going to use a little bit of time in our algorithm to fix up our data a little bit. And that might mean reversing its order, and it certainly means filling in that first cell. Okay, now, what's the algorithm for doing that? It's simply swap A over, then it's pull W out and swap B in, and put W here, right? It's swap of B and W, and then it's swap of whatever comes next, U. I guess there would be a U here, and this one is D. So it's a swap of D and U. It's just reversing the list. You can do like this. So what's the running time of that? What's the running time of that process? What's the running time of it? It's linear time, okay? It's linear time. Reverse and fill 0. This is big O then. I'm going to keep talking about that number 3 a little bit. Yeah? 2 says, well, can't you see? I'm kidding. It says repeated, remove min. Sorry, I'm sorry. All right, so 2 is repeated, remove min. I can't believe you can't read that. Okay, I have a question for you. Yes? That's exactly why I wanted to keep talking on number 3. It's sort of like we talked about this ahead of time or something. Right, exactly. Observe. We could have gotten these things in the right order to begin with, right? If we had just used a max heap instead. But my argument is that we kind of don't care because we only incur a little bit of additional running time to fix it up anyway. The other thing is that if we didn't want to have left over that need to fill in this spot, we could have implemented the whole heap so that this spot wasn't there. It's just that our child functions and our parent functions would be more complex. So all of that additional processing of getting the array ready to hand back to the client, it's number 1, avoidable with just a little bit of cleverness, and number 2, not very expensive even if we aren't so clever. So it's an issue of where you want to spend your dimes, I guess, or your cleverness. Okay, does that totally answer your question about it? Okay, yeah? Oh yeah, that would be fine too. Yeah, so you could completely get rid of that step if instead you mapped the client's index into the, the different location, but that demands that you have access to that. It demands that you're not trying to do this in a vector, okay? It demands that you are actually controlling the implementation of your linear structure, okay? All right, good questions. We're good. Any other questions about this? All right, so I have deliberately left blank the running time of item 2 because it's the answer to that that determines what I write down for the running time of the whole thing. What does your instinct say that it is? What does your instinct say that it is? N log n, right? Because if it were order n, why would we ever talk about any other sorting algorithm ever, right? If this were a linear time sort, it would be, there wouldn't be, oh, here are all these millions of different ways of sorting. It would be, here's how you sort. So we also would not be talking about it if it was like bubble sort, if it was n squared sort. That would be crazy too. So the only reasonable guess as to the running time of this thing is n log n. And given what we've observed before, it is this step that has to induce it. And in this case, in remove min, every time you deploy the algorithm, you may incur the full height, the cost proportional to the full height of the structure at that time. The whole structure, not the subtrees, not the cost of a subtree. So that's what's different between this analysis and the analysis of build heap, okay? I'm going to leave that there for you to chew on. So the running time is big O of n log n. The question is, why do we need another sorting algorithm? The answer is that it is equal to the best algorithm that we know about so far for sorting. So it's equally as fast as, what am I going to write here? Merge sort, good. And it's easy to implement in place. We don't have to do anything fancy to keep track of our memory like we have to do an in-place sort for merge sort. So it's easily implemented in place, and that place is an array, so it's very fast. Okay? It's harder to do. You have to have a bunch of additional supportive structures sort of emulating pointers in order to do that in merge sort. Okay, Notice that you guys did an in-place merge sort for MP3. That was, you didn't move data around at all. What you did instead was move around pointers. And the thing that costs you time in that context is dereferencing all those pointers. So if we put your code for MP3 against heap sort would win because, on large amounts of data, because your implementation for merge sort has to dereference a lot of pointers, and this can just pull big chunks into memory at once and use them. All right, so this is why we need another sorting algorithm. It's easily implemented in place. Yeah, that's it. Any other questions about this? So I believe that merge sort is still used because it is a stable sort and this one is not. And by that I mean if two equal keys are in a particular order in the original data set, they will be in that order in the sorted data. This does not assure that, but that's kind of outside the scope of what we're talking about here. All right, any questions about this? Okay, do you want to talk about quicksort at all? Or you're happy not talking about quicksort? Okay, so suffice to say, quicksort, worst case, really, really bad. Of course, we all use it in practice because it's very rare that it incurs worst case behavior. So, all right. I think if I were you, this slide would frighten me. Raise your hand if you are simultaneously taking CS173. Okay, so it only marginally scares you guys because you're like, okay, this is all fresh. Raise your hand if you have not taken 173 at all and you're winging it anyway. Okay, so the remembering CS173 together with let R be an equivalence relation. I don't know about you, but if I hadn't had a discrete math class, I'd be a little frightened with that. Okay, so this is pretty gentle though. I think it will be okay. And you know what, heck, when I was in 173 and the instructor said, I never took it, but when I was in the equivalent class, and the instructor said, let R be an equivalence relation, I went, so, you know, it's not that bad. I'm just kidding. I mean, I'm not kidding. I'll tell you why later. All right, so here's what we're going to do. We're going to talk about equivalence relations, and then we're going to design an abstract data type that supports particular functionality on that equivalence relation, okay? So just to refresh your memory about what an equivalence relation is, I'm going to define one for you. The domain is the set of students in this room, and we're going to say that two students are related to one another if they have the same favorite among those things. I'm looking for somebody with their cell phone out. Show me if you have your cell phone out. I need it. I need this. Okay. So look at the people with their cell phones out and tell me what game they're playing. No, nobody? So there was actually a person last hour. He goes, I'm playing Super Mario W. What does W stand for? I don't know. Okay. So the puzzle is, what are those? The puzzle is, what are those? The same favorite among, this slide was made about a year ago, at which time this one stood for Agario. Oh, so what's the FB? No. Flappy Birds. So it was getting pretty dated even at that time. So that's a little, how about this one? Temple Run, yep. Do you know Temple Run makes me car sick? Seriously. CC? CC makes me laugh. I have no idea what the original one was. I think it might have been Cookie Clicker, because I think that's what was popular when I made this. But since then, you know, among my, yeah, there's You know, though, Clash of Clans has been persistent for a really long time. It's amazing. So I'm going to say this is Clash of Clans. This is Pocket Minecraft. And I don't know what goes here. What's another game?
Madden.
Super Mario what? Run. Okay. Okay, fine. Okay, so I need a couple volunteers. So I want you all to think, what is your favorite among those games? And now you better go try them all so that you have an opinion. Oh, wait, that's not what I want you to do. Don't do that. Choose one. If you don't know, choose one that you do know. If you don't know any of them, choose your favorite letters. And I need to talk to a couple people. It's time to go. I can't believe this. Where did today go? Oh, we'll start here next time. Sorry. Shoot, this was going to be so fun. You found pizza.
I got pizza.